Today we will be talking about MRI, or magnetic resonance imaging. This is a non-invasive and non-destructive analytical technique, which is mostly known for its use in the medical field. But today we will see its uses in the field of chemistry and chemical engineering. Without further ado, let's dive into this piece of engineering brilliance and let's discover how it can be used. First off, MRI uses the quantum mechanical property of hydrogen atoms called the spin. You may have learned about electron spin before, but protons also have spin. As hydrogen atoms can be found in almost everywhere, it allows us to image a lot of different things. The nuclei have spin up, or positive half, or spin down, a negative half. This property called spin makes the hydrogen nuclei behave as bar magnets, which all create their own magnetic field and have a magnetic north. The direction of this magnetic north is determined probabilistically. Normally, this probability is evenly distributed, and the resulting magnetic field from all hydrogens cancels out, giving us a net zero magnetic field strength. This, however, changes if a strong external magnetic field is exerted on the hydrogens as they start to align with the magnetic field. The MRI then sends a radio frequency pulse which can flip the protons 90 degrees. As this is not the favorable position, they will try to again realign with the magnetic field. There are coils inside the MRI machine which can pick up a signal, as a moving magnetic field will create current inside these coils. The protons do not realign with the magnetic field on a straight path. They exhibit a spiraling motion when returning to the most favorable orientation. The frequency of the rotation can be described using Larmor frequency. As we see, it is dependent on the gyromagnetic ratio gamma and the field strength. From those two, we can adjust the field strength. A higher field strength leads to a higher frequency and thus also a better signal. By the way, the radio frequency pulse also has to have this frequency to flip those protons 90 degrees. We can use this to image different slices in the MRI machine. By using gradient coils, the MRI can slightly change the strength of the magnetic field throughout the machine. Let's place our chemical reactor in the MRI. We can see a varying magnetic field along the reactor. Let's say we want to image the slice indicated in red. Then we need the Larmor frequency of the hydrogen nucleus at 7.001 Tesla, and we get a result of 298.1 MHz. This is the radio frequency needed to image this slice. The MRI machine at the TUE can produce a field strength of 7 Tesla. The field strength of 7 Tesla can only be achieved using superconducting materials. These materials' resistance reaches zero when temperature is near absolute zero, allowing to create a very strong electromagnet. Usually, MRIs use liquid helium to cool the superconductor to 4 Kelvin, as the boiling point of liquid helium is around 4.2 Kelvin. This is also why the cost of operating this machine is high, as it has to be constantly kept at this temperature. Protons in different environments have slightly different properties. One of these is T1 relaxation, which is the time for the proton to return to its initial position after being disturbed. In this animation, the magnetic field vector can be seen when the proton returns to the original position. The other property is T2 relaxation, which shows the time of atoms going out of phase with each other. On the top right, you can see if there was no dephasing, then the signal would be constant. In reality, the system is very complicated, and the atoms interact with each other's magnetic fields, causing them to go out of phase as seen on the bottom right graph. These T1 and T2 signals depend on the material being used, which allows us to adjust our measurement depending on the area of interest. To get a T1 weighted image, radio frequency pulses are being sent out quickly, as this does not allow for the hydrogen atoms to go out of phase. To get a T2 image, the radio frequency pulses are sent at longer intervals, as this allows the atoms to go out of phase. These parameters have to be carefully adjusted to get the most out of your measurement. To make matters even more complicated, the signal received is the sum of all individual signals created by the hydrogen nuclei. Fourier transformations are used to deconstruct this complex wave into a summation of simpler waves. But to create a 2D grayscale image, another set of gradient coils are needed. These coils can adjust the phase of the hydrogen nuclei inside the slice currently being imaged to create specific patterns. One of these patterns can look something like this. On a simplified level, the patterns indicate the phase of the hydrogen nuclei. If we take the white part to be the benchmark, then the atoms in the white region are in phase. The black regions are then exactly the opposite phase, meaning 180 degrees out of phase. All other shades of grey are somewhere in between then 0 and 180. We can visualize this by pixelating the pattern and assigning each pixel a corresponding value to the color. As you can see, the phase shift is small in the white areas and high in the black areas. By sending many different types of patterns for the current slice using the gradient coils, the MRI creates a weighted grayscale image, combining all these patterns based on the signal received. This is exactly the reason why at the start of imaging you can see a lot of noise, which is filtered out as more patterns are added together. Finally, you get a 2D grayscale image of a slice. This is repeated for all the slices, and in the end a 3D image can be constructed when combining these slices. On the screen can be seen the construction of a 3D model of a human head using 2D slices stacked on top of each other. In the university, it is used to study reactor 1-phase and 2-phase flow. The MRI is a lot smaller than a medical MRI, but the field strength is also stronger. By using velocity mapping, the efficiency of reactors can be studied, and it is a great tool to study chemical reactors. Now let's take a look at the instrument itself. As mentioned beforehand, the MRI creates a strong magnetic field, so anything that is made out of magnetic material should be left outside the closed room to avoid injuries and destruction of property. In the video you can currently see the sample holder, into which a reactor is placed, and then the whole contraption is placed into the MRI. The overall schematic of an experiment involving 2-phase flow in a trickle bed reactor can be seen here. Now let's take a look at the reactor itself. It is filled with particles and can be of various sizes. This is one example of them. The reactors can be filled with particles of different shapes depending on the requirements and purpose of the experiment. The operation and setup can be done from the following windows. This is very complicated and requires extensive training to operate properly. Thank you for watching, and as always, good luck in the lab.